Take it away.
So today my topic of presentation is wavelength conversion of quantum dot photon with cold Caesium atom in a hollow core fiber. So this is the outline of my talk. I'll just give a brief introduction of what our project, because this topic is just one part of what our grand goal project. Then I'll define like how we are going to do it, like what we are going to do it. That is like wavelength conversion scheme and what we are going to implement it, and what all are things which is required to do these things like hollow core fiber and quantum dots. And then how we are doing it, that is the theoretical and numerical investigation and defining details. So first the introduction, like what is the project details. This is like we want to interface the quantum dot single photon with the atoms, and so to couple the light from the quantum dot, because quantum dot has a large bandwidth, approximately 1 gigahertz, and the atomic has a megahertz range. So to interface this, it has really a challenge. So it requires a large optical depth, means large number of atoms per cross section. So for that, we have a laser cooled atom confined inside a hollow core fiber, which will increase the optical depth of the model. So we wish to convert this photon wavelength, which is around this 894 wavelength, to telecom wavelength, which is 1469 in cesium, and 894 to 794, which can be used for satellite quantum field distribution. So first, I'll just give you like what are the two fibers, because there are two different wavelengths is need to be. One is in NIR range and another is in telecom wavelength. So two fibers are required, two different fibers are required. So first fiber is like 7 micrometer bandgap fiber, which allow us to transmit this wavelength range like 725 to 895. And the second one is like 30 micrometer fiber, which will allow us to give like transmit the wave, like a large wavelength, which is around 400 to like 1600. So this 30 micrometer fiber can be used for transmitting this, converting this 894 wavelength to 1469. So these are the two fibers, but most of my talk will be limited to this conversion of 894 to 794. This is our present goal to achieve in the 7 micrometer fiber. In future, we like to do this 894 nanometer conversion to 1469 telecom wavelength conversion. So before going into this wavelength conversion scheme, I just want to go into what are this, from where we are getting this are single photons. This is a nanowire quantum dot, which is indium arsenic phosphide quantum dot embedded in the indium arsenic nanowire. So these quantum dots like emits around this 894 wavelength, which is D1 line of cesium atom, and they offer a bright source of single photon and tangled photon pairs, and they are on demand, and they have like pretty, in comparison to the other quantum dots, you see like self-assembled quantum dot, their bandwidth is not that broad, like it's approximately less than 1 gigahertz, like so. And this tapering end of the nanowire will provide us to give us like the Gaussian profile and also increase the collection efficiency. So this, because it minimizes the reflection loss at the tip, so just provide us to increase the collection efficiency and then provide us the clean Gaussian transfer spatial mobility. And also it will help us into coupling to single mode fiber. So these measurements are all done in this cryostat, which is cooled at temperature of 4 Kelvin. And then with the confocal microscopy setup, you will collect the light from this quantum dot. Quantum dot is inside this cryostat. You collect the light from this quantum dot and then you couple it to the atomic system. So these are the few features of this quantum dot. Like we have found this quantum dot which emit the wavelength around 894.6, which is cesium. So it was really hard to find it because it's like there are thousands of quantum dot here. So luckily we found one of the quantum dot which is around 894.6. We characterize it, like we perform its second order correlation measurement, like G2 correlation measurement, and we found it's less than 0.5, which exhibit like it has single photon characteristic. We do its lifetime measurement and its lifetime is 850 picoseconds, so it's less than 1 nanosecond. So it's not that broad, like it's less than. And along with this, we also perform the power measurement and see like, okay, this is a photon we are looking for it. So this all is the experimental work we have done, and we found like, okay, this we are good to go with this kind of photon. So now coming back to my topic, like, so this is the atomic system, like in which it has a third non-linearity, so which allow us to like drag these four wavelengths by a four-wave mixing process in this diamond scheme. So in this case, this is the like single photon phase. So you want to convert this 894 to the other single photon state, which is around 794 or rather 49. If you choose 8s half scheme level, you can have to convert it to 794. If you want to choose 7s, then you can convert to 1469. So along with this, you need like to, in order to conserve this energy and momentum conservation in this diamond scheme, you have to supply two pump laser, which is like, it's a classical like strong pump laser around this 852 and this 761 wavelength. And these are the like the detunings of the corresponding detunings, like delta A, delta B are the detunings of the corresponding to the pump. This delta B and delta S are delta A and delta B are detuning corresponding to the pump, which is omega A and omega B, their RV frequency. And this delta I and delta S are the detuning corresponding to the input and output signal respectively. So we first start with this quantized field propagation equation. So you have Hamilton-Lenzman equation, so which is given by this equation. So you have to find this interaction Hamiltonian. And once you find this interaction Hamiltonian, you can use it to find this sigma under the steady state solution, and then you can get this quantized Maxwell equation. And once you solve this quantized Maxwell equation, you can get the coupled wave equations. You get a coupled wave equation, and these coupled wave equations are coupled in both the like EI and ES things, like the input and output signal, they are coupled to each other. So you, in order to solve it, you have to provide a proper solution, like they are interrelated to each other. They are not properly independent with each other. So you have to optimize and do a global search to find like how, like what are the parameters you need to feed it so that you get a better efficiency. So we first scan it for like, and these like alpha and self-propagation, and they are all depending on these parameters only, like this or Rabi frequencies of the pump and the detuning parameters of like two pumps and the detuning parameters of the input and output signals. So now we perform the global search for these one. Like, so first we fix the laser power. So we fix the Rabi frequency of the pumps like 350 megahertz respectively, and we fix the optical depth, and we then do the scan over this detunings of the pumps and the detunings of the input signal. So we find like this, there are several parameters which will give us the efficiency of more than like 90%. And using these like parameters, we'll again try to find like how much is the bandwidth of these efficiencies. So we will now you see like what is the role of this optical depth on the bandwidth, like how much bandwidth we can expect to get it. So once we have a like a lower bandwidth, like lower optical depth, like let's say 100, first of all, like for lower optical depth or higher optical depth, like you can get a various parameter, like let's say for first set of parameter, you will get a different bandwidth. Second set of parameter, you will get another bandwidth, but with the same efficiency kind of. So all the efficiencies are same. So in this way, like even for thousands also, it's just like once you increase the optical depth, your bandwidth is going to increase, but with a different set of parameters. Like so 5 set of parameters giving you the different bandwidth as well as, but with the same efficiency. So in collate this result, this is like, I'll give some time on this plot. So this is the plot with respect to full width, half maxima, and versus optical depth. In this thing, this color plot defines your efficiency, and this gray line defines the optimized parameters or the bandwidth for this particular optimized parameters. So we see like higher the optical depth, you are getting better efficiency as well as your bandwidth is also increasing. So for like 10,000 optical depth, you get a band like full width half maximum of 800, around 801 gigahertz bandwidth. So in this case, we say like if we have a higher optical depth, we'll be able to get a better bandwidth, which is required in our case because the quantum dot has a larger bandwidth. So we again search for, let's say if we have a quantum dot wavelength exactly at 894.593 nanometer. So if we don't have any detuning, like let's say delta is 0, like there is no detuning in this. So then we get a better efficiency if we scan in the megahertz range. But if we keep on increasing the detuning parameters, like let's say we increase in gigahertz, 1 gigahertz, the efficiency drop down for if we scan in 300 megahertz. But if we extend our scan in gigahertz, then we're able to get a better efficiency. So the question arises, can we do it like, can we extend and scan the search in gigahertz? Like, is it allowable, permissible limit for omega and omega B thing, like the Rabi frequency? So we then perform the simulation and perform we vary the Rabi frequency with respect to the power for this fiber, which is for 794, 894 to 1469. And we find that even for like 10,000, like 1 gigahertz frequency, it can be like just 1 milliwatt power is required in fiber. So it's kind of permissible in it. So it's okay to scan it like more than in gigahertz range, like it's roughly around gigahertz. So it's the same thing we are applying the other wavelength range, and we find that the same thing like with the 1 gigahertz Rabi frequency for both, either like this pump or control, both control pumps. Like the pump power is like 1 milliwatt approximately for 1 gigahertz. So we are not like limiting its case, like it's still permissible to go with it. So the next thing is like we all do this thing in continuous wave approximation. Now, if we do go for a like pulse propagation, and we start with the 5 nanosecond. Like our aim is to find for the 1 nanosecond, but as a check, we start with the 5 nanosecond Gaussian pulse. And we find that when we go for 5 nanosecond with the optical depth of 3000, we get like efficiency of 0.99. And all the searches are like in the range, like it's in gigahertz range, within gigahertz range, less than 1 gigahertz range. And when we extend, like when we increase our optical depth from 3000 to 5000, our efficiency goes up to like roughly approximately 1 for the wavelength conversion efficiency for 894 to 794. So now we switch to the from 5 nanosecond to 1 nanosecond. And we find like with the same optical depth, like 3000, its efficiency is dropping down because we are broadening the pulses, like it's 1 nanosecond. So our efficiency, so we search for 5000 and in efficiency we are like, it's 80%. So if we go for like 10,000 optical depth, we'll again able to get like one approximately 1, like we approach to the 1, like, so, and still the range is it's still in the gigahertz range, like it's not more than gigahertz, so it's okay, like we can achieve, like these values are achievable in real life also, like it's not hard to achieve it. So I think like if we go for 10,000, then that's like be able to go it, and 10,000 is it like is kind of permissible because in our case, like the atoms are loaded in hollow core fiber, so the interaction is confined in a smaller area, and so we're able to achieve it. Like we are pretty hopeful for that one. So I think that's what we are trying to achieve here. So I think this, and so we again, so we just see how this wavelength is, like how these signals are like propagating in the length, along the length. So as you see, like at first, like it's like fully like the input signal is and the output signal is 0. But as it goes along the distance, the input signal is converting into the output signal fully. Like it's around 80% is converted fully. So at around 5000 optical depth. So this is just a one notation, like one simple. So I think in summary, I can say like that we did perform the theoretical investigation for the conversion of the 894, which is the quantum dot wavelength, to the 794, which can be used for satellite transmission in quantum key distribution. And the same way we can perform for 894 to 1469, which can be used for transmission in fiber network. And with high optical depth, it can be realizable, like it can be achievable with the permissible data. So I think that's it. And at the end, I'd like to acknowledge like this to Professor Bajcsy and Professor Bharadwaj, and these are the project contributors. And I'd like to acknowledge the fundings. Thank you.
Thank you very much. Are there any questions from the audience? So in an experiment, what keeps the atoms from being absorbed onto the inside of the fiber? Is it so that the light forms a sort of repulsive barrier around the sort of hollow core, or?
No, the atoms are first cooled for the laser, and then it is dropped in the fiber actually. It's a free fall dropping in the atom.
And they don't get absorbed onto the fiber, and they remain sort of sitting in free space in the middle of the fiber.
Some of them, it's not like all of them will drop to the fiber. Some of them will absorb, but yeah, like most of them will remain there in the fiber.
The fiber needs to be really straight, I guess.
Yeah, the alignment of the atom with the fiber should be like.
I see. So it's not that the light in the fiber also acts as some sort of waveguide that keeps the atoms in the middle, or anything like that. The atoms are just freely propagating inside the fiber.
Atom is freely propagating inside the fiber, but there's also there's a I think magic trap. There's a one wavelength is also, which is also not. You have to provide that.
Yeah. I think there's a question from Shrish, perhaps.
No, it's not a question. I just wanted to reply to your question, maybe to clarify.
Okay, go ahead. Yeah.
Like she mentioned, like Dr. Divya mentioned, the magic wavelength trap. So if there's a magic wavelength trap inside the hollow core fiber, the atoms can be confined in the vacuum region without hitting the fiber wall. So if that magic wavelength dipole trap is on, that can guide the atom through the vacuum. So that's one way to at least try to not let them hit the fiber wall. But I suppose there are other ways as well. Yeah, just wanted to clarify that point.
Thank you. Are there any other questions? Or I'll ask another one. So Divya, so you in your simulations, you want to talk about how you did the simulations?
So like this continuous one is like analytical, like.
Oh, it's analytical.
Yeah, so we
You
just
solve these coupled equations analytically.
Yeah, it's followed by this reference, and we've solved this like unless the steady state. Yeah.
Okay, so I mean, you must have made some assumptions, or.
Oh yeah, so the steady state assumption is like the population is in the ground state, and excited state, like the combination, like they are oscillating between this ground is in excited state, and like the steady state I've already told, the energy conservation, like they are energy conservation there, and
And so how much do you know about the mode structure of the light inside the fiber? You know all of that.
so it's a Gaussian.
It's a Gaussian. I see.
Structure is Gaussian inside the fiber.
But you're treating the atoms as it's a sort of single particle problem. The light, there's no other collective effects.
The atoms we are treating as a collective operator, like.
Thank you. Shrish, is that your hand still up, or is it up again for a second? That's down. Okay. Okay. Are there any more questions? All right. Well, thank you very much. I will